January 27th, 1986, 11:45 at night. A fax machine in Huntsville, Alabama prints a single document. The final formal authorization for Space Shuttle Challenger to launch in 28-degree weather. The coldest launch ever attempted. 22 degrees colder than any previous shuttle flight. 7 crew members are asleep in crew quarters. 1 engineer in Utah is still awake. Roger Boisjoly sits at his kitchen table, writing 2 words in his notebook. Coffin corner. He knows what happens at dawn. 73 seconds later, he will be right. The question is not what caused the disaster. The question is why the people who knew exactly what would happen were ordered to stop talking. That is exactly what we are going to find out. The space shuttle is the most complex machine ever built for regular operation. 2 solid rocket boosters, external tank, orbiter, 144 separate systems, 51 missions completed since 1981, designated man-rated hardware, certified safe for human flight. The certification rests on a single engineering assumption. Every component must survive every credible failure mode. If one part fails, backups engage. Redundancy, multiple seal rings, secondary containment, layer after layer of protection, unless the failure is criticality 1. Criticality 1 means no backup, single point failure, loss of vehicle, loss of crew, immediate, catastrophic, unsurvivable. In 1982, NASA engineering documents classify the solid rocket booster joint seals as criticality 1R. R for redundant, 2 O-rings per joint, primary and secondary. If one fails, the other holds. The rating is based on ground test data. Static fire, controlled conditions, standard temperature. The classification allows the shuttle program to continue. By 1985, flight data tells a different story. Post-flight inspection shows erosion on primary O-rings. Black soot past the first seal. Damage increasing with each cold weather launch. Engineers begin testing O-ring behavior at low temperature. The results are unambiguous. Below 50 degrees Fahrenheit, the rubber compound loses elasticity. It becomes hard as a brick. When the booster ignites, the steel casing flexes. The joint opens. The O-ring must expand to fill the gap within 0.6 seconds. If the rubber is cold, it cannot move fast enough. The gap stays open. Hot gas escapes. The secondary ring is supposed to engage, but the joint flexes so wide in cold conditions that the backup seal cannot reach the sealing surface. No contact, no seal, no redundancy. Criticality 1R becomes criticality 1. The engineers know this in the summer of 1985. Roger Boisjoly is a senior engineer at Morton Thiokol, the contractor that manufactures the solid rocket boosters. He has worked on the O-ring seal problem for 2 years. He has run the temperature tests. He has reviewed the post-flight damage reports. He has calculated the joint dynamics. In July 1985, 6 months before Challenger, he writes an internal memo to Thiokol management. The subject line reads, "Help!" The text warns that if the seal problem is not fixed, it is a jump ball as to the success or failure of future missions. He uses the phrase, catastrophe of the highest order. The memo is specific. It names the joint. It names the temperature threshold. It names the risk. It requests immediate action to redesign the seal before the next cold weather launch. Management receives the memo. No redesign is authorized. No launch constraints are imposed. The flight schedule continues. 17 more missions are planned for 1986. The fastest launch cadence in shuttle history. NASA is under political pressure. The agency needs to prove the shuttle is operational, reliable, routine, not experimental. The Teacher in Space program is part of that narrative. Krista McAuliffe is selected from 11,000 applicants. She is trained, she is scheduled. The mission is 51L. The launch date is January 28th. President Reagan is scheduled to deliver the State of the Union address that night. The mission is mentioned in early drafts of the speech. The pressure is not documented in writing. It does not need to be. Everyone in the program understands the context. Delay is failure. Delay is admitting the system is not ready. So the missions continue, and the damage reports continue, and the engineers keep testing, and the temperature threshold keeps appearing in the data. 50 degrees. Below that line, the O-rings do not respond. January 27th, 1986, morning. The forecast for the Florida coast drops. Overnight low, 22 degrees. Daytime high, 31. Far below the previous coldest launch of 53 degrees. That mission, 51C, showed significant O-ring erosion on post-flight inspection. Now the forecast is 22 degrees colder. Thiokol engineers in Utah see the weather report. They immediately contact management. A teleconference is scheduled for 5:45 Eastern Time. 2 locations: Marshall Space Flight Center in Huntsville, Kennedy Space Center in Florida, Morton Thiokol in Utah. 14 engineers, 9 managers, NASA officials. The meeting begins with Thiokol presenting engineering data. Boisjoly walks through the temperature analysis. He shows charts correlating cold weather launches with O-ring damage. He shows lab test results. He shows the joint dynamics. He shows the seal timing problem. He shows the loss of redundancy. The conclusion is unanimous among engineers. Do not launch below 53 degrees. Recommend delay until temperatures rise. The engineering case is clear. The data is unambiguous. Every engineer on the call agrees. Then NASA responds. Larry Malloy, manager of the Solid Rocket Booster project at Marshall, is frustrated. He asks when Thiokol wants him to launch. Next April? The sarcasm is noted in later testimony. Another NASA official challenges the data. He argues that the temperature correlation is not proven. He argues that the O-rings have been damaged on warm launches too. He argues that the seal has never actually failed. He shifts the burden of proof. Thiokol must prove the shuttle will fail, not prove it is safe. The engineering standard is inverted, guilty until proven innocent. What nobody notices yet is that Morton Thiokol is a contractor. NASA is the customer. NASA awards the contracts. NASA controls the flight schedule. NASA evaluates contractor performance. The structural incentive is to say yes. At 6:15, Thiokol management asks for a 5-minute offline caucus to discuss the recommendation. NASA agrees. The line is muted. What happens in that 30-minute caucus becomes the hinge point of the disaster. Thiokol senior management is in the room. Joe Kilminster, Vice President of Space Booster Programs, Bob Lund, Vice President of Engineering, Jerry Mason, Senior Vice President, Cal Wiggins, Vice President and General Manager. The engineers are also present: Boisjoly, Arnie Thompson, Brian Russell. But the managers immediately make clear that this is a management decision. They poll only the managers. The engineers are not asked to vote. Boisjoly tries to argue. He brings out photographs of previous O-ring damage. He lays them on the table. He explains again why the cold makes the seal dynamics worse. He is cut off. Thompson supports him. Same result. The engineers are told that the data is inconclusive, that the shuttle has always worked before, that NASA needs a launch. The managers talk among themselves. Bob Lund, the Vice President of Engineering, is hesitant. He is an engineer by training. He understands the data. He does not want to sign off. Jerry Mason, Senior Vice President, speaks directly to him. The quote is recorded in congressional testimony. Mason says, "Take off your engineering hat and put on your management hat." Lund reverses his position. The managers vote 4-0 to approve the launch. The engineers are not counted. At 6:50, the caucus ends. Thiokol unmutes the line. Joe Kilminster reads the new recommendation to NASA. Morton Thiokol reassesses previous position. Temperature data is inconclusive. Recommend proceeding with launch. NASA accepts. The teleconference ends. Boisjoly goes home. He writes in his personal notes that the launch is heading into a coffin corner. Bob Ebeling, another engineer on the call, goes home and tells his wife it is going to blow up. Alan McDonald, Thiokol director of the Solid Rocket Motor Project, is physically at Kennedy Space Center for the launch. He hears the final recommendation over the phone. He refuses to sign the formal launch document. He tells his boss he does not want to be the person to stand up in front of a board of inquiry and explain why the launch went forward against engineering judgment. His refusal is noted. Kilminster signs instead. The fax is transmitted at 11:45. The launch is approved. January 28th. Overnight, the temperature at the launch pad drops to 22 degrees. The service structure is covered in ice. Large icicles hang from the gantry. The ice team inspects the pad at 1:30 in the morning. They report concern. A second inspection at 7, then 8, then 10:30. The ice persists. Engineers worry about ice breaking off during launch and striking the orbiter. NASA managers decide the ice is acceptable. They do not revisit the O-ring question. The cold is visible. The cold is measured. The cold is photographed. The decision stands. At 11 o'clock, the astronauts board. Commander Dick Scobie, pilot Michael Smith, mission specialists Ellison Onizuka, Judith Resnick, Ronald McNair. Payload specialists Gregory Jarvis and Krista McAuliffe. They strap in. The hatch closes. 11:38, liftoff. The solid rocket boosters ignite. High-speed film cameras capture the event in slow motion. At 0.6 seconds after ignition, a puff of black smoke appears from the aft field joint of the right solid rocket booster, exactly where Boisjoly said it would. The smoke is vaporized O-ring material. The seal is failing the instant the engines fire. The puff lasts 2.5 seconds. Then it stops. Not because the seal has resealed, because combustion byproducts and aluminum oxide temporarily plug the gap. The shuttle clears the tower. It pitches, it rolls, it climbs. Boisjoly watches from Utah. He counts the seconds. He knows what is happening inside that joint. 58 seconds. 59. 60. The shuttle passes through a wind shear layer. The vehicle flexes. The temporary plug in the joint breaks loose. At 64 seconds, a small flame appears on the side of the right booster. It grows. At 70 seconds, the flame burns through the external tank attachment strut. The booster separates. It pivots. The nose strikes the external tank. The tank ruptures. Liquid hydrogen and liquid oxygen mix. At 73 seconds, the external tank explodes. The orbiter is torn apart by aerodynamic forces. The crew cabin separates intact. It arcs upward, then falls. Impact occurs 2 minutes and 45 seconds later. All 7 crew members are killed. The disaster is televised live. The investigation begins immediately. President Reagan appoints the Rogers Commission. Former Secretary of State William Rogers chairs the panel. The members include Neil Armstrong, Chuck Yeager, and physicist Richard Feynman. The commission interviews hundreds of witnesses. They review thousands of documents. They hold public hearings. On February 10th, Alan McDonald testifies. He describes the teleconference. He describes his refusal to sign. He names the managers who overruled the engineers. His testimony is detailed, specific, damning. He is immediately reassigned within Thiokol. His career in launch operations is over. On February 25th, Roger Boisjoly testifies. He brings his memos. He brings his charts. He brings the photographs he tried to show management during the caucus. He explains the temperature threshold. He explains the joint dynamics. He explains the seal timing. He explains the loss of redundancy. He explains the exact failure mode that caused the disaster. He is asked who made the decision to launch. He names Jerry Mason. He names Bob Lund. He names Joe Kilminster. He repeats the management hat quote verbatim. The hearing room is silent. The testimony is broadcast. Boisjoly becomes the face of engineering integrity. It destroys his career. Thiokol management isolates him. Coworkers stop speaking to him. He is assigned to meaningless tasks. His office is moved. His files are seized by company lawyers. He takes medical leave. He is diagnosed with depression. He never works in aerospace again. But here's the thing. The O-ring failure was not a surprise. It was predicted, in writing, 6 months in advance, with specificity. And the prediction was not ignored because the data was unclear. The data was unambiguous. Lab tests showed 100% failure rate for O-rings chilled below 50 degrees. Post-flight inspections showed escalating damage correlated with cold weather. The joint was already classified criticality 1, meaning no margin for error. The engineers unanimously recommended delay. So why did the launch proceed? Not because of a technical mistake, because of a deliberate management decision to redefine what counted as proof. Under normal engineering protocol, hardware is proven safe before flight. The burden of proof is on the launch advocates. If you cannot prove it is safe, you do not fly. NASA reversed that burden on January 27th. Thiokol was told to prove the shuttle would fail. Not might fail, would fail. Prove the disaster, not the risk, the disaster. That standard is impossible. You cannot prove a catastrophic failure before it happens. You can only show the risk. The engineers showed the risk. They were told the risk was not proof. So the launch was approved, and 73 seconds later, the proof arrived. Feynman understood this immediately. During a televised commission hearing on February 11th, he performed a demonstration. He took a sample of O-ring material. He compressed it with a C-clamp. He placed it in a glass of ice water. He waited. After a few minutes, he removed the clamp. The rubber did not spring back. It remained compressed. He held it up for the cameras. That was the failure mode, exactly as Boisjoly had described, exactly as the lab tests had shown, exactly as the engineers had predicted. The teleconference records were subpoenaed. The memos were entered into evidence. The timeline was reconstructed. NASA Administrator James Beggs had been placed on leave in December due to an unrelated legal issue. His replacement was Acting Administrator William Graham. Graham had been in the role for less than 2 months. He did not attend the teleconference. He was not informed of the engineering concerns. The decision loop bypassed him. The launch was approved at a lower management level. When the commission asked who was responsible, the answer fractured across multiple officials. Everyone claimed they did not have full information. Everyone claimed they were relying on someone else's judgment. The official chain of command could not identify a single decision-maker. The system was designed to diffuse responsibility. That diffusion allowed the launch to proceed without anyone formally overruling the engineers. The engineers were simply excluded from the final vote. The Rogers Commission report is published in June 1986. It identifies the O-ring failure as the physical cause. It identifies the flawed decision-making process as the organizational cause. It makes 9 major recommendations. Redesign the joint, improve communication, include engineers in launch decisions, establish independent safety oversight. The report is damning, but it stops short of naming criminal negligence. No one is charged, no one is fired for the decision itself. Some managers are reassigned. The shuttle program is grounded for 32 months. The boosters are redesigned, the joints are strengthened, new seals are installed, heating elements are added to keep the O-rings warm. The changes work. When shuttle flights resume in 1988, the joint performs as designed. No further failures occur. 78 more missions are flown over the next 15 years. The fix proves the engineers were right. The failure was preventable. But here is where the official narrative breaks. The disaster is remembered as a technical failure, a flaw in the hardware, an unfortunate engineering oversight. Museums display the redesigned joint as the solution. Documentaries focus on the explosion, the 73-second flight, the crew cabin falling into the ocean. The story becomes a tragedy, a reminder of the risks of spaceflight. What gets erased is the meeting, the 30-minute caucus, the management vote, the engineering hat quote, the muted phone line, the refusal to count the engineers, the inversion of the burden of proof. Those details appear in the Commission report. They appear in congressional testimony. They appear in Boisjoly's memos. But they do not appear in the public memory. The disaster is not taught as a failure of authority. It is taught as a failure of technology. That reframe protects the system. If the problem was the hardware, the solution is better hardware. If the problem was the decision-making structure, the solution is dismantling the hierarchy that allowed non-engineers to overrule engineers on technical safety questions. That solution was not implemented. The same management structure that approved Challenger continued. 16 years later, Space Shuttle Columbia disintegrated on re-entry. 7 more crew members dead. The Columbia Accident Investigation Board found the same organizational failures. Engineers raised concerns about foam strikes during launch. Management dismissed the concerns. Engineers requested imagery to assess damage. Management denied the request. The engineers were overruled. Again. The system did not learn. It could not learn, because the system was not designed to elevate engineering judgment. It was designed to meet schedules, control costs, and satisfy political stakeholders. Safety was a constraint, not the objective. Roger Boisjoly spent the rest of his life trying to teach that lesson. He left Thiokol in 1987. He could not find work in aerospace. He was formally qualified, experienced, decorated, but no contractor would hire the man who named names. So he became a lecturer. He traveled to universities. He spoke to engineering students. He showed them the memos. He walked them through the teleconference. He explained the management hat moment. He told them that technical integrity is not enough, that being right is not enough, that having the data is not enough. You also need the authority to say no. And if the system does not give you that authority, the system will kill people. He died in 2012. His obituaries called him a whistleblower. He rejected the term. He said he was just an engineer who told the truth. The truth was in his memos in July. It was in his charts in January. It was in his testimony in February. It was always there. The truth did not save the crew. It saved the program. The boosters were fixed. The shuttle flew again. But the people who overruled the engineers were never held accountable. Jerry Mason retired. Bob Lund retired. Joe Kilminster retired. They received pensions. They were not prosecuted. They were not banned from the industry. The consequences fell on the engineers who refused to lie. Alan McDonald was eventually reinstated after public pressure, but his launch career was over. Boisjoly never returned. The institutional incentive was clear. If you approve a launch that kills people, you retire quietly. If you refuse to approve that launch, you are destroyed. That is the hidden function of the Challenger disaster. Not a cautionary tale about technical risk, a demonstration of organizational power. The disaster showed that management authority supersedes engineering judgment, even when lives are at stake, even when the data is clear, even when the recommendation is unanimous. The engineers can be right and still lose. That lesson was transmitted to every engineer in every aerospace program in the country. You can raise the issue. You can write the memo. You can present the data. But if management decides to proceed, your job is to comply or leave. Boisjoly chose to stay and tell the truth. The system made an example of him. Not through formal punishment, through isolation, reassignment, seizure of files, silent exclusion. The message was clear. Technical integrity will end your career. The Challenger story is taught in engineering ethics courses. Students learn about the O-rings. They learn about the teleconference. They learn about the management hat, quote. Then they graduate and enter the same system, the same hierarchies, the same incentives. And when they raise a safety concern, they learn what Boisjoly learned. Being right is not protection. The system does not reward the engineer who stops the disaster. It punishes them. The engineer who warns is remembered as a tragic hero. The managers who ignored the warning are remembered as footnotes, if they are remembered at all. The structure survives. It is still operating, right now, in aerospace, in automotive, in medical devices, in construction, wherever engineers report to non-engineers, wherever schedule and cost override safety, wherever the burden of proof is inverted. The same meeting is happening. Different project, different product, different engineers, same outcome. The people who know the risk are excluded from the final decision, and when the failure occurs, the story will say it was unforeseeable, tragic, a flaw in the design, not a flaw in the system. The engineering profession calls Challenger a landmark case. The landmark is a warning. The system that killed 7 people in 73 seconds is still in place. It has better O-rings now. It does not have better authority structures. The engineers still cannot say no. They can only write memos and count the seconds and hope someone listens before the next launch. Roger Boisjoly spent his last 25 years saying that hope is not a strategy. He was right. He is still right. The shuttle is retired. The lesson is not.